Hi folks, this is the video tutorial for chapter 14 of my textbook, Composites Finite Element Analysis Essentials for 3D Experience. And the title of the chapter is Continuum Shell Elements for a Simple Laminated Composite. So let me explain to you what the problem is. Earlier in chapter 10, we analyzed a sandwich panel which was made of carbon epoxy face sheets and a foam core, and this panel was subjected to a bending moment of 500 inch-pound on both sides. This problem was solved with conventional shell elements, and what we want to do today is repeat that problem, except that we're going to be using what is called the continuum solid elements. Okay, so the dimensions are given here, the thicknesses are there, and the material properties are shown on the right-hand side. These are the same things that we did in chapter 10. So there, instead of we created a surface representing this strip and then meshed it with shell elements. Now here, we're not going to do that. We're going to create the actual solid block, which later on we're going to uh, in that block, we're going to define layers, namely two plies for carbon epoxy and one ply for foam, and measure solid elements, and we're going to solve the problem. Okay. Now, notice that when you put 500 pounds on both sides, the structure is in equilibrium. However, it can move as a rigid body. Therefore, I'm going to be using the 1, 2, 3 rule, just like I did in chapter 10, in order to take the rigid body motion away and solve the problem. Obviously, that's going to bend something along this line. Okay. All right, so let's go ahead and do that. I already went to the part design because we're going to be creating obviously a solid object. I already created. I went to the part design and renamed this part to be video chapter 14. And now we're going to make that part. So on a convenient plane, on that horizontal plane, I will sketch a 4-inch by 1-inch rectangle. That's going to be basically our strip later on once we pad it. So let me dimension this. This is going to be 4, and this one is going to be 1. Okay, exit. And now pad it by the total thickness. Now total thickness is the thickness of the two face sheets and the thickness of the foam, which is 0.35 inches. So we pad this by 0.35 inches. So this is basically my part. It is my part. Okay. Now let me create a coordinate system over here because we're going to need a rosette. So uh, ordinarily I move this thing away from the part so that it gives me more leeway in order to move around the screen. But in the book I left it there, so that's fine. So there is my coordinate system that's going to be used as the rosette. Now, the other thing I need to do is to extract the bottom surface of this block, because later on when we go to composite design and try to create plies within the block basically, I need a surface. Remember, for plies you need to create ply groups, and the ply group requires a surface. Okay, so in order to extract this bottom surface, what I need to do is to go to the uh, generative shape design. As soon as you say surface, you have to go to for example, generative shape design. Okay, and under the transform tab, there's a transform tab. Look where the boundary is, but expand this thing. There is an extract, and you go and select the bottom. This surface is going to get extracted, and we say OK. Now, if you want, you can change the color of that so that it's easier to distinguish. So properties, graphics, I'm going to change that thing to yellow because let me actually change it to, how about orange, okay? You can see that. All right, good. So save everything. The next step is to create our materials. So we're going to go to Tools, under Material Browser. Let's create materials. I'm going to call carbon epoxy, video, chapter 14. Okay. Now, as soon as I do that, a material is created with that name, so I can specify the properties here. So right there. Okay. So right click, composites. Okay. Now notice that when you do this, these are all the defaults that are going to come up. Now the first one, I'm going to change it unidirectional, although this is strictly cosmetic. It has nothing, no impact on my FEA calculation. This is the cured thickness. The cured thickness for the carbon epoxy is 0.05 inches. Now I can put 0.05 inches and move on, but I don't have to. I can put any dummy thickness, for example, 1 inch. And when I do that, for the foam, I have to put 5 times of that, because if you look at the actual part that we have, the foam is 5 times thicker than the carbon epoxy. So I can use 0.05 here and 0.25, or I can use 1 and 5, or I can use 3 and 15, etc. to convince you, because the thing with the continuum shell elements is that based on the actual part of the object, is going to figure out what the correct thicknesses should be. As long as you have the correct ratio, relative thicknesses, it's going to do it. And on purpose, I'm going to make this thing 5. That's how I did it in the book. But if it's confusing you, just put the 0.05 and make sure that for the foam, you put 0.25. But I put a dummy cured thickness here of 1, and I say OK. Now we're going to do the simulation data. Okay, and this is going to be a lamina. The values are 20 e to the 6 for E1 psi. This is 1.2 e to the 6 for E2 transverse modulus. Poisson ratio is 0.25, and these are 800,000, 400,000, and 400,000. Okay, so there is the material that I created for carbon epoxy, and I'm gonna do another one. So another one is called foam, chapter 14, or video. This is so that I can easily find them if needed later on. Chapter 14. Okay, and we say okay. So there it is. Right click, composite. Again, remember these are all dummy, except that here I insist on putting 5 inches. This is not the correct thickness. The correct thickness is 0.25 inches. But I need to maintain the correct relative size, relative ratio. So if carbon epoxy was 1, this foam is going to be 5. And the good thing about the continuum shell element is that based on the thickness of your actual part, it's going to figure out what the correct thicknesses should be. And we say okay. And then for material, for the simulation data, so I go to mechanical, elasticity, elastic. Now this I'm going to treat as isotropic, because it is isotropic foam. So the Young's modulus is 10,000 psi, and the Poisson ratio is 0.45. It's coming from that data that we had before. Okay, so this is done. You're going to save everything. Remember, I need these two materials at my disposal. So what I do is I go there to material definition. And as soon as I do that, it brings the two materials that are in session and puts it at my disposal. I can easily go between the part and the material editor where I have these things. Okay, so the next thing we want to do is to create our composite properties. So let's go ahead and do that. We go to excuse me, composite design. We're going to do the apply design, composite parameters, add a material, library, and this is where this material editor is very handy. You click on it, and the first one is carbon epoxy right there, and it's going to populate. It's going to populate my my table here. You can see that this is carbon epoxy video chapter 14, and here is the unidirectional, and this is the cured thickness, wrong cured thickness 1. Okay, and then again add the material, go there, and select foam. Okay, so there's the foam. You can see that. Don't worry about this thing says bidirectional. Please, this word bidirectional means nothing. These are all cosmetic. I just forgot to change that thing to unidirectional, but these are not used in our FEA calculation. And the cured thickness, wrong cured thickness is 5 because the ratio should be 1 to 5. Okay, and now the rosette. Add the rosette, and there's coordinate system. Here's the rosette that it's going to put. Okay, very good. And I think we're done here. All right, good. Now that we created our composite properties, we're going to do plies group. Now this is what it's going to be asking you for the surface. Remember, we created the surface extract, or I can move this thing around, take it from down here. It really doesn't matter. I need the surface. You will not be able to select the faces. You will not be able to select the faces of the block. Okay, good. And the draping direction, by the way, was upward, and that's what I want to keep. You can see that. See that draping direction is up. That's what I want to keep. Okay, good. Now we're going to create our plies, one by one, 3 of them. First one, in that ply group, the boundary is that sketch. The boundary is that sketch, and the attribute is carbon epoxy, and all of these are going to have zero fiber direction. Now remember, for the face sheets, I want to make him 0. For the core, because isotropic, it's a dummy thingy, so I'll make everything 0. Okay. All right. This is for ply 1. Another one going there. The second ply is going to be your foam, but the boundary is the same. This is going to be foam angle dummy angle 0. Okay. And the last one, which is the ply on the very top, ply 3, boundary is the same, attribute is carbon epoxy, and the angle is 0. Okay, so now remember, these have the wrong thicknesses. So if I go to ply exploder, I can look at it, but it may look weird. So let's see now, because the ply exploder doesn't know that. It's going to basically use dimensions 1 and 5, so it's going to be a gigantic stack up on top of each other. So let's try to see how it looks like. Okay, you can see that this is all ridiculous, but that's because the values that I have for thicknesses are ridiculous. Cancel that. It's okay. There's nothing wrong with it. It's just that Ply Exploder does not do a good job when I try to look at it. All right, let's save everything. We're done here. We're done here. So we're going to go to mesh this thing. So we go to structural model creation right there. Do not use automatic. Use none. Because you're going to actually, if you actually say automatic, as I've done in the past, what it does, it's going to take this box and mesh it with tetrahedral elements. I don't want that, so I say none. In other words, don't use any mesh. Don't do any meshing yourself. So we say okay. Okay. Now we're going to do the meshing. So go to mesh, and I'm going to use partition hex mesh. So you click on this, You select the body, it turns yellow. You can only do first order elements. In other words, 8-noded Breck elements. You can only do first order elements. You cannot do this. If you did this, it's going to come back when you run it. It says, oh, I can't do it, etc., etc. And the size, I'm going to use 0.3 inches. Okay? Remember, this thickness was 0.35. I'm going to use 0.3 inches. Mesh. And this is what. If you use a smaller one, it's going to stack up other elements on top of each other, which is fine. There's nothing wrong with it. But I want to just use one layer through the thickness. If you use something smaller, then maybe 2 or 3 layers through the thickness. Okay, but in the book, I've done only one, so I just kept that. All right. Now, notice that there's no properties here. The mesh has been generated, but no property. So I go to Model, as in the past. You expand the sections, and you want right there. In the past, when you use shell elements, we use continuum shell. Sorry, not continuum shell. Right. Sorry. What I meant was that we use not continuum shell. It was composite. Yeah, this is what we used before. No. Wait a minute. Composite shell section. This is what we used in the previous 13 chapters. Okay, composite shell, because we only got shell. But now we have composite continuum shell. Okay, this is the one. This is continuum shell is when you don't have any composites. So I want composite continuum shell. You click on it. Okay, first of all, for the support, you select that mesh that you created right there. And for the composite, you have different options. Let me say plies, by plies. And as soon as you say that, it says, okay, go select your ply group. There's only one. So I select this, okay. And that's pretty much it. You don't have to worry about any of these other stuff. So we just leave it the way it is. So we say, okay. And now we have a shell section, we have a section 2. All right, so let's save everything. We're now going to go to scenario. It's a structural problem. You get 2 red exclamation marks down here, as in the past, right there. So first thing that you do is you're going to go to setup. You select your finite element model. It gets rid of the structural, gets rid of this. So you have to select that. This becomes a green check mark. Then you go to procedure, a static problem, and make sure that you uncheck the include geometric nonlinearities. None of the problems that I did in the past 14 chapters, 13 chapters, I included that because we're assuming that this behavior is linear, okay? And it's going to be faster to run, etc. There's no convergence issues. Okay, now we're going to do the loads. Okay. Now, first of all, if this is bothering you, you can always hide it, hide the elements right there. Let me try it again. Well, I think I closed that. That's okay. I can always hide it from here. Right click, hide. There we are. So the first thing that we're going to do, we're going to apply a moment. Now we have to apply a torque, a remote torque, right there, remote torque, right there. You select on it. You select that face. It puts a coordinate system. Obviously, you have to apply 500 units of torque or moment about the y-axis, and it's going to be negative. Pay attention to your coordinate system because depending on how you create your model, yours may be different, okay? We want to apply the moment about the y-axis like this. If you go back to the to this drawing, you can see that, okay? All right, so minus 500, say okay. And then you turn it around, do it on the other side. By the way, if these things are bothering you, hide them. Another remote torque on this face, this time is 500. Okay, there we are. Okay. Now we have to apply some restraints because otherwise this will fly away. So we go to restraints, the way I've done it in the book, the 1, 2, 3 rule. Okay, you have to select this corner. Now make sure you hide some stuff that are blocking you for picking these things. So first of all, hide the stacking, hide the sketch, and now you can go and select probably this. You still cannot do it, and that's because you have to hide the extract probably. Hide the extract, and I pick it now. Something else is blocking it. Oh yeah, this coordinate system. These coordinate system are blocking it. Let's hide it. Oh, undo. Okay, so let me do it from here. The coordinate system, I'm going to hide it from here. Still something is blocking. Let's check. What else can be blocking here. Uh, is this hidden? I'm not sure if my sketch is hidden. Sketch, hide it. Now it's hidden. And now I can select it, right? I thought I already hid it, but that's not the case. So I select this corner point. All three coordinate directions are restrained. Then I do one on this side. It cannot move in the direction X or direction Z. And finally, over here, to avoid it rotating about that edge, so I'm going to fix this corner point from going in the Z direction. Okay, before I run it, I'm going to ask for some additional data. So I go to simulate, additional data, right there, additional output. I'm going to ask for stresses, and I don't need these, and that's pretty much it. Yeah, and do it by layers. Oops, right here, by layers, and give me all three, top, bottom, and middle, because if you don't ask for this information, it'll give you only on the top and the bottom. If you want the middle, just ask for it. Okay, save everything. And let's go ahead and first do a model and scenario check. Make sure that everything is okay. Okay, very good. Then do a simulation check. I may get a warning, one or two warnings, but as long as it's not an error, don't worry about it, unless it doesn't run. That's a bad strategy, but let's move on. Okay, it's going to be very fast. Now remember, if this geometric nonlinearity was included, this would, they may have to iterate, you know, it will do it incrementally, and yeah, no errors is what you're aiming at. Okay, worked fine. And finally simulate. That's going to be fast. Chapter 15 will also deal with this continuum shell elements. You may want to look at the book to see what are the drawbacks and what are the advantages of using continuum shell elements. Imagine that if you had a aircraft fuselage, which was part of it was made out of, I don't know, composite material, and you had to mesh it with these solid elements. So just think about it. Okay, so this is von Mises stress overall, bottom and top. So first of all, let's look at deflection, displacement right there, but not at the frame one. Frame one is no low load. There we are. This is what we expect. And there is the deflection, 0.023 inches. Now, von Mises stress, although you can get it like that, first of all, it doesn't surprise you. This is all constant, okay? Uh, go back to, if you go back, you see that for this type of a problem, we have moment at the two ends and nothing else, the stresses are constant in the layers. But to get within a particular layer, you double click on this and you go and say, okay, what is it that I want? I want component as component, not the overall, but for example, informational, let's say the foam. Here's this apply tool as the foam. And I don't want the top and the bottom. Maybe I want just the top. And I want, what is it that I'm looking for? Let's say I'm looking for uh, stress along the fiber, okay? Well, foam does not have fibers, of course, but that really is irrelevant. So notice that's 15.3 psi. Now, if you go to the ply 1, or ply 3, let's go to ply 1, same thing, it's going to be substantially bigger than this, okay? Apply, you can see that it's 38,000, and that is the role of a sandwich structure. In other words, the core, which is very weak, is not going to take the in-plane and the bending stresses, okay? It will take the transverse shear load, but not the bending. So remember, the stress in the foam was 15. The stress in the carbon epoxy is 38,000. And then you can do other things. You can do, for example, this one is ply 3. Now, the other thing I want to show you is that if you go to thickness, nominal thickness, apply 178. This is not the real thickness. First of all, it shows it in millimeter, but it doesn't matter. What the 178 millimeter is remember, I said I gave it dummy thicknesses, 1 inch, 5 inch, 1 inch. That's 7 inches. 7 inches is 178 millimeters. So these are all dummy numbers. But if I go to ply thickness, not the nominal one, layer thickness, apply, this is correct because the total thickness, two face sheets, and the foam was 0.35 inches. 0.35 inches is 8.89 millimeters. I just forgot to change the units here so it shows the 2 inches. Okay, folks, so that takes care of this video segment. Good luck.